Welcome, everyone. Today, this is Fred Shankelberg, and today we're going to talk about reliability apportionment. And in the chat window, just before we're getting started, it looked like it was very timely for a couple of people and hopefully informative for everybody else. It's not a new topic in reliability engineering or even in project management. Yet I think it's worth talking about because there's many different ways of going about doing apportionment, and my intent is to help you focus on where the real value or the real benefit of doing a reliability apportionment or allocation process is all about, and just some ideas and hints about how going about doing it. So let's just dive in here, and please do keep the chat window closed. I've got a slew of different questions for you and comments that I'm looking for your input on this, because by no means am I the expert at apportionment. I've done it a few times, and it's usually starting with a reliability goal. There's something that we, as a program or as buying a piece of equipment, we want this item to last for some duration without failures or with some minimum number of failures for a repairable system. And so we typically have an overall system goal, and that's all well and good. And the idea is that there's all kinds of different parts inside these systems that we're dealing with. And for example, a vehicle, if you lose the water pump, you lose the vehicle. If you get a flat tire, you're delayed. You have to repair that. Some systems aren't as critical to the primary function, but if my stereo or the radio system didn't work, I'd probably consider it a failure and investigate having it repaired in some fashion. And so we do reliability engineering and design products to meet those reliability goals, including all of the various subsystems that make up our products, such that we can have happy customers. And there's lots of benefits for doing that. Now, let me digress just a moment and tell you a quick story about how important apportionment really is. And this is some years ago. A client of mine had called me or engaged me to help them figure out how to improve their product. They were having, I think, 50% of their products that they'd ship would come back as a failure within a year. And they were saying, well, we set a goal, we let everybody know what it was, we did failure modes and effects analysis, we did halt testing, we did a lot of testing, and everything seemed to check out for the overall system goal. But I did receive more than one phone call, oftentimes after hours, where it started with, Fred, I need your help, because they were just getting overwhelmed by the number of failures. And to make a long story short, and I may have told this before in a previous webinar, but with a little bit of investigation, we asked the different members of the team, and this was a medical device, and it had electronics and some pneumatic pieces and a compressor and a couple other major subsystems like a power supply and so on. And each team understood the system goal and designed their part to meet the system goal. So the compressor was good to have maybe a 5% failure rate or better at 2 years. But each and every subsystem was designed to meet the system goal. And they were actually pretty good at doing that. They actually, each individual team optimized their part of the product to just meet the reliability goal. And so we did a little bit of quick math. It was a series system, so any failure would cause a system failure. And lo and behold, because the, say, 5 different elements all met the system goal, but not anything better, they actually achieved the field reliability that they designed for. Not what they wanted, but what they designed for. And so instead of designing a product that was at 95% reliable over 2 years, they actually designed a product that achieved about a 47% reliability over 2 years. And it was because each of the subsystems actually came in at about 95% reliable over 2 years. And so it was a pretty serious problem and probably just a simple miscommunication. And it's really a big part of where uh, apportionment and how we use it really comes into play. Now, why else, other than minimizing field failures, why else would you use reliability apportionment? And this might be a little bit ahead of the game if you're not familiar with what this process is. But for those of you that are familiar with it, jump on the chat window and how do you use apportioned reliability or budgeted reliability or allocated reliability? I see Brian's typing. Predict maintenance costs, good. Yeah. And hopefully, Brian, you're not using MTBF. I know that's a way to do it, but I find it not that terribly helpful for predicting changing failure rates over time. I have to mention MTBF at least once. It's this thing. Yeah, expectations with with a contract design team. So if you're outsourcing the design, certainly you need to specify what it is you're looking for. Yeah, thanks, Brian. Appreciate that. Yeah, so the apportioned reliability is part of setting the overall goal, right? And modeling and a bunch of other things. Yeah, looking for where you're going to have issues. It can fit into your risk analysis, like FMEA and other pieces too. It helps you understand uh, where the reliability performance is actually coming from. What are the pieces that go into it? Good. All right, so I'm going to step back just a moment, and it seems like a good number of you, the ones that have replied so far, are familiar with apportionment, but let's just go back just briefly and talk about what it is for those that may not be familiar with it. Essentially, it's a budget. It's like we would do with costs, right? Let's say we're making a car, and we have so much of a purchase price that we're aiming for. Say it's a $20,000 retail price vehicle. Well, once you take out advertising and the profit and the dealer's slice of this and the commissions, and I'm just making up numbers here, those in the auto industry can tell me, but let's say we have to make the actual physical vehicle has a budget of, say, $10,000 to make it. And the engine and the powertrain might cost us $3,000 or $4,000 to actually physically make it, to pay salaries, to buy materials, to do the fabrication, the design work, all of those other pieces. And so reliability is the same way. If we want that same vehicle to survive for 10 years or so many miles with a relatively low failure rate, well then how many times is that powertrain allowed to fail or expected to fail? And so if overall we want to have, say, only 3 incidents where the vehicle fails over 10 years, well then where are those coming from? And so at least in the vehicle I have, I'm hoping it's not going to happen in the sound system or anything else actually. But I do know that something will fail. And there's thousands and thousands of components within that vehicle that are all competing to cause failures. And so the powertrain sees one set of probabilities of it failing. And by design and by its maintenance, we can tailor that actual probability of failure. We can define what that is. And so setting a budget is basically saying, well, what's the goal for that specific part? What's its probability of failure? Now, one thing to keep in mind is that each part of that vehicle is going to have a different environment. The under the hood environment is dramatically different and rather uncomfortable as compared to in the cabin. In the trunk or under the boot, I think in some parts of the world, it would yet be another environment. And so different weather, different use profiles, different frequencies of use. And so as you define the budget, the reliability goal for each of the subsystems is keep in mind that you need to do a complete reliability goal for that. That includes probability, environment, use profiles. What's that function? The powertrain's function is completely different than the stereo system. Yet, they probably are both expected to have a similar duration, say 10 years. But their probability of failure is probably, no pun intended, going to be different. So think that through as you start budgeting out where are all the failures going to come from or expected to come from. And so there's a lot of parts in a vehicle. How would you go about doing that? What would you actually budget? What measures or metrics would you use to actually do a reliability allocation or a budget? Let me see if I got I might be ahead of myself a little bit, but the idea here is and I think I answered it inadvertently already, is it's reliability. Just if I want 95% reliability at the system level and I've got 5 subsystems, well, what combination of reliability of those subsystems, when multiplied together, is the probability of failure, their reliability values essentially, the probability of successfully operating, will equal that 95% or better. And it's really that simple. Now, if you get a more complex program or something, it gets a bit more tricky if you have parallel systems and so on. But the other thing to consider here, and we'll come back to this a little bit later, is you can budget, say, for mission critical aspects of it. So the primary function of a vehicle is to provide safe transportation. So the braking system, the fuel system, the powertrain system, all of those elements, steering system, all of those subsystems to the vehicle may be going in our overall budget or allocation process to come up with that system level. And then we may have secondary type functions like the sound system or air conditioning system and other things that if they fail, you can still get to the store and back, for example, or get to work and back, but you may lose some customer satisfaction because of those failures. And so they may get a secondary level of allocation or budget for yet another system goal. So there's a number of different ways you can slice these, and it's pretty flexible. It really depends on your particular situation is how you put it together and what makes sense for your team. We'll come back to that in more detail. Now, in a vehicle, like I mentioned, there's thousands of components, but even in a desktop computer, there may be 1,000 or so components when you add up individual resistors and diodes and connectors and cables, and you could even think of the ink on the cable within your computer that identifies that particular cable as being a part of your system. Now, the failure of some things within a system may go completely unnoticed, and so it may not make a lot of sense to set a specific goal for that. Or it's kind of the rule of the 80-20 rule is, well, where's the bulk of our failures going to come from? Which ones do we need to pay attention to? And it kind of goes back to that old adage of, people will do what you measure. So if we set goals for the major subsystems or major components or modules, so think of a computer, it'd be the monitor, the motherboard, the power supply, those specific subsystems. Yet within that system, you may have some critical components like the microprocessor, the main chip within your computer, may have its own specific reliability goal. And it's just a matter of organizing those such that you can tally it up, essentially, or multiply the reliability values together to get an estimate of your system goal. And so we'll talk about the modeling part a little bit later. But you could break it down by module and not go any further down. Just go to power supply. But if the power supply team or your supplier may have that goal that you provide them as a computer designer, let's say it's 99% reliable over 5 years for the power supply, they may break that 99% reliability down even further to the analog ASIC, to the various capacitors, the various elements within the power supply, and set specific goals for that. So think of it as a set of cascading groups of goals that all should tally up to meet your system goal. And the setting of how much detail you put in the apportionment is to the level that makes sense for you and your team in order to make decisions. And this is probably my primary point through this presentation, is that it's a flexible tool. And if going to the major modules of your system or the major subsystems is good enough for you and your team to make decisions, then that's where you stop building out the model and doing the apportionment. Now, if you go to every single component, it's a lot of work, and there's a significant diminishing return to say set a specific reliability goal for every diode on your computer. If you have to determine what its local temperature is, for example, and you can do that. You can use an infrared camera and you can map out the temperature distribution across your circuit board. Yet the difference in temperature is not really going to change the outcome of any decisions you're going to be making. You're going to certainly want to put those components on your board. The overall motherboard is likely not going to fail because of a few diodes. It might, depending on your design. So setting the goals, the breaking it down to the various sub-levels of or elements within your product, is an exercise in balance. Where is it that we're making the most decisions? And then set the allocation level to that level so that your team has the information, the subsystem goals, that help them compare it to and use it for the decisions that they need to make. So we talked about computers and mentioned cars. There's a whole slew of products out there today that include software. Now, I'm biased a little bit because I'm primarily a hardware engineer and I've worked with systems and hardware. Yet, in the reliability allocation, let me ask it this way. Would you set a goal for the software elements of your product? And if so, where would you put it? Where do you include the software reliability in an allocation model? I grab my pen here, see if I can get that to work. Software included in the subsystem. Yep, I've seen that done. So if I'm talking about the, say, the ASIC, the main ASIC, and there's firmware built into that chip, a failure of the firmware is a failure of that chip subsystem. If there's software driving your power supply, for example, or your monitor, the screen itself, we'll use the screen. There's usually device drivers in those, and if those fail, then you count it as part of that subsystem. That makes sense. I've seen that many times. Yeah, and Sean, I agree with you, as I often find that software is neglected. Now, what else should we include in our model? I'm going to draw just a very simple model here. Oops. If I can get curves to work here, I have to go slow. So here's my system. And I'll abbreviate reliability. I use R-bar as an abbreviation for reliability. And let's say I'm fairly confident that all of us are going to include hardware. And I mentioned software. And I agree with Sean, is that it's not often included in an allocation model. I think we're past the point where people don't believe reliability affects or software affects reliability. You just have to visit your local call center to realize how many times customers complain about software related failures. And sometimes they're not obvious where it comes from. But what's the third major class that can cause failures? Yeah, right. And you're right. There's a number of different ways to do it. Yeah. And Google site problems is one of them. We could call it software or apps or user interface, those kinds of things. What's another element? Misuse. Yeah. Uh, I've seen organizations that look at their field data and classify 25% of the returns as no trouble found, and another 25% of the problems as abuse. And so I think they're missing a big part. There you go, Michael. Human factors. So it's the user interface in Google, and you were close to that. The applications we're using with it, the control panel, the display, and just in construction is how does a person interact with your product? And they can cause failures that the hardware, say a button, is perfectly functional. The software responds to the button press and does exactly what the designer expected it to do, but the button is in the wrong location and it causes failures and customer dissatisfaction. And so as you build out a reliability allocation, it's really easy to look at hardware and say, well, I have a power supply, a monitor, a motherboard, those major pieces of it. Oftentimes, we either ignore the software and don't look for or account for the reliability impact it has, or we embed it, no pun intended, right in the hardware systems that support those particular aspects of the software. Yet the one that we often miss is human factors. And yet it can cause a significant number of failures and interactions, mistakes with your product or customer dissatisfaction. And one other element, and this is, I saw a webinar last week where they used this a notion of a pro tip, but is leave, what I suggest is if you're building out an allocation, is leave a little bit of headroom for the uncertainty. Say 5 or 10% of your overall allocation goes to unassigned. And it makes everything else have to be a little bit more reliable, a little harder to achieve. And you have a little bit of extra room here to account for the things that we haven't accounted for, the unknowns. It's not uncommon to ship a product and have some failures that we never anticipated or had seen before. It's usually not a lot if you're doing due diligence, yet if you don't account for those, then the rest of the system isn't robust enough to overall meet the system reliability goals. And so the basic idea of a allocation model is that it's a top-down model of your goals. You just say, here's my system goal, and I break it down to the various subsystems to a level that makes sense for your application. We often talk about then the bottoms-up estimates or modeling of a product, where we take, say, a variety of different ways of estimating the reliability of our product. Now, setting the goals by themselves really doesn't help a whole lot. It provides some awareness, it provides some information, but if we're not measuring it, if we're not creating well, where are we today, allows us to make a comparison to the goal stands alone and doesn't really help us make any decisions. So working at those subsystem levels, and this may impact how detailed you go in setting out the allocations, is can you measure it? can you estimate the reliability over the durations of interest? And that then gets placed next to your allocated goals. And very quickly you can see that some elements will meet our goals and it's not going to be an issue. Other parts are we don't know how well it's going to perform versus our goals, and we need to improve our measurement of it. Or the third case is, well, and I'll pick on power supplies, is we know the power supplies are not reliable enough, and we're going to have to invest in making improvements there. And it's that comparison that sets us up to make decisions. And so the first, if you make a program that does nothing but measure reliability, you need a way to make comparisons. So doing the goals and allocation goes a long way to make that happen. Right? And so the next part of this is then, well, how do you actually create this model? Right? So it's getting back into this practical side is a little bit of background about what these models are about. Is do you organize it by say the bill of material, which is at a very detailed level, down to individual screws and washers and things like that? Or do you organize it by major subsystems? Or what other ways would you organize the information within your reliability model, this allocation? Major subsystems, yeah. Functional wise, right. So like a vehicle is I have a powertrain. I have, or if I'm on a factory piece of equipment, it may have hydraulics, and it may have electronics and control circuitry. It may have um, uh, other features to it, the mechanical systems of it. Yeah, field replaceable units, especially if you're doing a system that's repairable, like you're mentioning, Scott, is those kinds of things really help with um, understanding like setting up spares and replacement and repair units and so on. That works great. Yeah. And Brian, I often do it software as its own part of a block diagram. If nothing else is to and get the discussion going is how the software can impact system reliability. And I think you've all hit the things I've listed, except maybe the location in the system. So in some organizations or some products, it may make sense to look by where it sits within the system or what step in the overall process of its use. Is it, say, a process flow for factory equipment? So there's a variety of different ways you could organize it. The most common is by what's its primary function or who's the team that's actually working on it. And so if I have a mechanical engineering team, electrical engineering team, software engineering team, I may break it down into those three groups. And then within the mechanical, they may have the chassis and the internal structure and some other aspects of it. Say an inkjet printer would have the paper feed path as a part of the mechanical engineering system. So hopefully you get the idea that it's a very, very flexible process to assign the allocations. And there's no one set way that I know of that this is how you do allocation. It needs to be tailored to your team. And again, most specifically, in how you make decisions. Right. Now some of you may be familiar with allocation processes or standards. I know the military years ago has had a number of different standards on how to do allocations, and there's like 3 or 4 different prescribed processes for doing this. Do you really need a standard or an algorithm to sort this out? And you may have picked up on my tone there, you probably don't. Now, if you're under contract, somebody says, thou shalt use this particular standard, then you probably should use that standard. Yet I don't really find them all that terribly useful. There's a number of different ways to do these things, but the math side of it is actually pretty easy, right? And it gives you a reference, a starting point. I agree, Gulen, but I don't think it helps you achieve the objective. The standards can tell you how to turn a crank and do some calculations if you have sufficient input. But it remember that the objective of doing the apportionment and setting up this budget is to create a framework where you can make comparisons to where your reliability is currently estimated for these different parts of your system. And the ultimate goal is to help your team make decisions. Yeah, now I do use equal allocation. And it's more what I call just a guess. And the idea, or a straight line allocation is the way I would call it, is if I had 5 components in my system, give each of the subsystems, each of those components, the same reliability allocation such that the product of the reliability equals my system goal. So if I have 5 elements, I have to do a little bit of work with Excel to do the 5th root of my system reliability goal, and I get a number. More often, I don't try to figure out how to do these higher roots to find an equal allocation. I just set up a spreadsheet and do a little uh, uh, trial and error until I find a set of reliabilities that the product becomes the system goal. And it's an interesting process. Just at the start of your program, you might not even know what all the components are, say in the power supply or in the motherboard, using a computer analogy. The design is really still just in the concept phase, and maybe we have 5 major elements or subsystems, and we are just forming a system goal. Well, if we don't have any other information, it's just guess at what the reliability will be for those different subsystems. Now, the experience part can come from if you've got historical data or if you've got experienced engineers, they can give you some estimate or ballpark of how good they think this particular power supply is going to be or this particular motherboard is going to be. Some of the allocation standards say, well, how complex are the various subsystems? For example, if my power supply is very, very simple, but my motherboard is exceedingly complex, it doesn't make sense to have the same reliability expectations for both of them. Although I think that's a mistake because I've seen more power supplies fail than motherboards. But the idea is get something on the paper, get something started, and the intent here is to get the discussion going. So I did this once actually with a computer system. I think it was a workstation system, and they called me into a meeting to help them set up the allocation. And using a simple analogy of just a computer with, say, 5 subsystems in it, I did a little bit of quick math and I wrote a straight line allocation. And so let's say it's a 95% reliable over 2 years was the system goal, and let's say, I think it was, get my pen here. I always use this example, so I'm quite sure many of you have heard this one before. It's only because I can remember the numbers. But let's say I have a computer system and we're interested in get rid of that, a 2-year duration, and it's for, say, a home and office use type of product that's going to be used, and we want at least 95% reliable as a system level. Hopefully our computers these days are better than that, but let's say that's what we're getting. And so the power supply needs to be, with a straight line allocation, needs to be roughly 99%. Looks like a 7. And so on. If I take the product of 99 or 0.99 raised to the 5th power, I get just a little bit above 0.95. And when I actually did this, I knew that it wasn't a good allocation, that some parts of our system were much more complicated than other parts. And so the power supply folks immediately said, that's not possible. We can't afford to buy a power supply that will meet that goal. But the keyboard people, keyboard and mouse, right, they got real quiet. They were happy. They were smiling. They were going to be well above the goal of 99%. And so on the spot, we said, well, power supply, how good can you be? What can you, as a team, sign up for? And as long as it's not 95%, it has to be above 95%. And then we talked about the math real quick. They said, well, we can get 96.5. And this was just engineering guess. We didn't have a bunch of data. We didn't have a whole raft of information or anything else. And then, so he went down 2.5% from what the straight line allocation was. Well, that has to come from someplace, because now the product of 0.965 times 0.99 times 0.99, so on, is less than 0.95. So we don't meet our system goal if we achieve this allocated set of targets. And so what we did is we went back to the keyboard people and says, well, how good can you be? Can we make it up here? And they said, well, we can get 5 nines reliability. We're really confident. Our historical data, our experience, or whatever is really, really good. And then we do the math, and is that good enough? And maybe we had to increase a few of the other ones in order for the overall system to meet the reliability goal. That process took about 20 minutes. Now, of course, if you got a more complex system and there's more unknowns, then the ones that you just don't know, I just put a star on it and say, we got to get this number. Let's go figure out what a reasonable estimate is or a reasonable target is, and then come back and adjust the model as needed. But even a straight line allocation, it's not set in stone. It really, really is set up to encourage your team to start talking about the reliability for the particular elements within the product, within the system. And so if you've got historical data, hopefully I spelled that right, not hysterical, I think, as I did earlier in my draft, is take a look at how it's performed in the past. That gives you a good grounding as to how reliable you are likely to be going into the future. It gives you a starting point, if nothing else. And it's a step using your actual designs, your actual customers' use, and those kinds of things. So it's good if you've got it. It's a place to start. One application I did some years ago is we had a medical device, and this is a Weibull plot. So there's time on the x-axis, and from 0, let me get my pen, from none of them failed at the bottom to all of them failed at the top on the vertical axis. And the system level gave us, from a previous product, gave us a Weibull plot, and actually fit a Weibull fairly well. But as we broke down the data, we found that there was this compressor that had a wear-out mechanism. And there was installation damage, the chassis of the system typically failed early in the system when it was first installed, and then had a much lower failure rate over time. So its beta was less than 1, where the wear-out mechanism was much greater than 1. And at different time points, say the first month versus the first year, the priorities changed. The Pareto of what we were working on initially for the short duration, early failures, was the chassis. For later, we were working on the compressor to move that reliability further to the right, make it a better, more improved. And software, it is a very simple system, was in the noise. even if we doubled the reliability of the software and moved it to the right a significant amount, it really wouldn't change the overall system. And so think of it as create a Weibull plot for the overall system, and then plot each of the subsystems based on your historical data or your current estimates as a way to see how the dynamic changing of what's going to fail occurs over the life of your product. And so it's one way to use your historical data to set goals at, say, different points, say 1 month in 1 year. And then hopefully this becomes very clear, is if you first set one up in the concept phase, as you get more information, as your engineers work out the details of how the product's going to be designed and manufactured, as you start engaging suppliers, as you start getting test results, compare that to your allocated values and adjust as needed. It's not fixed in stone. It's a tool for you and your team to judge, are you on target to make your system reliability goal. Now, here's a question that some of you may have faced. When do you stop and say, do we have the right system goal? Would you change the system goal? And what would it take to cause you to make that proposal? Yeah, yeah, and of course that never happens when the customer changes their requirements. So yeah, that would be a good way to prompt that. Yeah. Let's say you're going through this process and you've set up your allocation, and let's pick on the power supply again, and they say, you know, for $13,000, we can get you a new power supply that will meet this allocated reliability goal of at least, say, 96%. And it gives a little more advantage for the other subsystems. Now, if we're selling a computer for $1,000, it's probably not a viable option, right? So we may be precluded from achieving our target because of the cost of the components or the design, or even just the base technology. Our system goal is often based on what we hope we can get to provide to our customers, or in some cases the customers demanded or expected, stated it explicitly. But there's no, it doesn't mean that we're going to achieve that. But as we learn information and we find whether it's cost or technology capability or engineering prowess that we're just not going to get there from here, well, it makes a good case then to say, well, let's adjust our system goal and go circle back to all of the stakeholders to make sure we're still there. Yeah, it's got to be feasible. Just because it's a goal doesn't mean it's absolutely possible. If it's set properly, right, and all of the stakeholders and the due diligence is done with the feasibility, then the goals probably are pretty solid. Now, it's a last resort, is can we economically improve other parts of our system to accommodate, say, a power supply that needs to drop below its allocated goal? Can we adjust for it within our system? If we can't, then we need to look at very seriously, do we have the right system goal? Yeah, and it really is a balance. Is it feasible? Is it the cost to achieve it, the cost of the downside if we don't? All of those factors come into play, and that goes into the larger discussion of setting goals. But this allocation process is just like setting a goal. The idea, though, is that you can change it. You can modify these at will to make it a useful tool to comparing to your estimates. All right. Let's take a look at a couple of really good uses of it. So one of them is if you set a goal, and I know a couple of you are looking at setting up test plans in reliability plans, and to a large degree setting up testing for the various parts of your system. So if I've got, say, that computer, and my keyboard and mouse have historical data that are at 5 nines reliability over the 2 years I'm interested in, there's not a lot of emphasis to, and the design's not changing, we should mention that also in any significant way. There's not a lot of reason to test the keyboard and mouse to verify that it's going to meet its targets. Even if we miss it, say instead of 5 nines we're at 4 nines, the overall impact on the system goal is fairly slight. On the other hand, if we're looking at power supplies, and we think we can make it at 96.5% reliable, but we're not sure. Well, that's a really good reason to do some testing for it. And now you have a target for setting up your test system, is that you want to demonstrate that you're at least 96.5% reliable over 2 years or better. And that will drive sample size and the style of accelerated testing and a variety of different parameters that go into doing life testing. Sample size is by far the most common question we get. So you may see that as a way to go back to your allocation and say, well, here's what we expect it to get to. Here's our goal. Here's what it's going to take to prove that we're there, and how many samples we need, and so on. But keep in mind is that it's not just the sample size going after the reliability target over some duration. It's also that the stresses change. The stuff inside the box are going to see different temperature profiles and use profiles than items outside the box or under the hood of the car versus in the cabin of the car. So by doing the allocation and thinking through all of the elements that go into a reliability goal, is now you have a set piece of information to help you frame what's the life set of stresses, or what's the number of activations, all of those kinds of parameters that go into it. And so it provides a set of information that you can use, one, to decide what elements need testing, which are critical or on the margin to helping you achieve the overall subsystem or the system reliability goal, or which ones have the most uncertainty. So either of those kind of conditions is a good case then to run that particular set of tests. If it's got historical data or it has little impact on the overall system level, you may reduce or eliminate the testing for those areas, because the information is not going to provide a lot of value compared to putting those resources in areas that are more likely to impact the decisions you and the team need to make. Now, it's a big project to go through this process for even a simple product to line up all of the testing. But it's really one step at a time, is work the allocations such that you can make decisions at the appropriate levels. If you're working with a supplier, what's their allocated reliability for the set of elements that they're providing or their subsystem they're providing? And so balance out how detailed your model gets to where you need to make decisions. And so it's iterative, very much so. And it takes a little bit of due diligence and a little persistence to work it to the levels that you need, but consistently rolling up the numbers to make sure that you're still on target to meet your system reliability objectives. So another good use of this is in working with suppliers, and a couple of you mentioned this already, is if you're going to give them a requirements document, well, include not just a make it reliable kind of statement or accept their data sheet reliability value, is say, we want your product to work for 2 years with a 96.5% reliability under these conditions. Give them enough information so they can make a judgment and help you determine, will their product meet your reliability expectations. They can't meet your expectations if they don't know what they are. So one of the uses of this allocation process is the communication with your major suppliers and design teams that you'll be working with. So give them enough information so they can help you. Now, This was a subject to a previous webinar. You can find it at reliability.fm under the Ascendo Reliability webinar series. But if they only provide MTBF, you're only getting one part of, say, 4 parts that you actually need in your allocation model. And oftentimes it doesn't account for what's the changing nature of that failure rate. Now, if it's the only thing you have and it's not a critical to the reliability of your system, well, it may not matter if it doubles in failure rate over the life of the product, but it's still insignificant. So you heard it here, is that in that case, MTBF and its associated failure rate may be good enough. Pick your battles. If it's the critical power supply for your system that's going to dictate what's the reliability of your overall system, well, then you need more information. And either it's coming from the supplier or you're going to have to do it yourself. The bottom line, though, is that we're setting up these allocations like we're setting a reliability goal for the system in order to make decisions. And that's what it's all about. And the intent of what we do as reliability professionals is help the rest of our team to make decisions, give them enough information so they can make comparisons and they can make and set priorities across the team. And that's a big part of it. Yeah, and Michael, you're exactly right. And I've seen this myself, is that some suppliers, they give you failure rate data, but it might be off of Mail Handbook 217 from 20 years ago. It's just on the data sheet because customers ask for it, and then once they see it there, they don't ask again, irregardless of how useful the actual values are. Others kind of give you a graphic that has real fat lines on it, so it's pretty vague as to what their reliability claims actually are, which in many cases is justified because they don't know how it's being used when they're setting up a data sheet or a generic reliability claim. And so, Ray, it looks like, how do you know what reliability you need? Yeah, and you're exactly right. If I'm a customer, I don't want my product to fail. Now, as a reliability professional, I know that products fail and that there is some acceptance of that in the marketplace in order for us to maintain a reasonable cost for our products. And it's a balance of that risk. And so for some products, say a consumer product that's, say, $20 and is mass produced, and if it fails, it really doesn't cause much disruption or harm or angst to anybody concerned, well, the reliability expectations for it can be very low. On the other hand, if it's, say, a life support system or the attachment mechanism of a wing to an aircraft, where a single point failure would cause the loss of the aircraft and everybody on board, well, that reliability for those pieces may need to be very high and may need to be very well understood. So it probably is subject to a whole nother webinar, is how do you set the right reliability for your circumstance? But it's the ultimate decision is your customers. You know, if they're not buying your product because, and the Yelp reviews are all, it's not reliable, you need to improve the reliability of your product. And I've seen this in a number of places, and there was a study that was done at HP, and it was for a networking devices. I want to say a switch or a router or a modem or some box like that. And they did a bunch of work to connect the reliability performance of the box. What was its reliability performance over 1 year, which is the warranty they had on it, versus customer satisfaction. And if they improved the reliability, customer satisfaction went up. If the reliability dipped, say for a particular model, its associated customer satisfaction changed. And so it had ramifications on repurchase, on retaining customers, on brand loyalty, on market share, all kinds of huge impact connected to its reliability performance. And so it became that balance. I think it was Brian that mentioned it earlier. It's a balance between what's the downside cost, the warranty cost, for example, of a failure versus the cost to improve it, or vice versa. What's the upside advantage to improving your reliability, and is it worth it? So in many cases, these become business decisions considering the customer's expectations, the technology, what are we capable of doing, and the balance over business goals. And so one last story here. One of the best uses of an allocation model I've ever seen or heard of was, I think I'm going to go to my last slide here, and then I'll go to the download slide as we end. A marketing manager actually came up with a very simple allocated model for the major subsystems of the, he was a technical marketing manager, and he sat with the team on this workstation in their weekly meetings. And he presented a very simple block diagram and said, here's the goals and here's what our current estimates are. And the program manager, she looked at that very simple chart and said, power supply, you're not meeting the goal. You're the weakest link. You're the least reliable estimate right now. What's it going to come back next week with a proposal, including cost, of what it takes for you to achieve the goal, your allocated goal? What are the options and how much is it going to cost us? And each week, this program manager looked at that model and against the allocated goals, the estimates versus the current allocated goals, and looked for the weakest link. And the entire team then focused the resources and efforts to, one, understand the current reliability estimate, improve the estimate, or two, to improve the actual design to help it meet its goal. Now, in some cases, that didn't work, right? They had to change the goal or allocate reliability to and from other parts of the system. But instead of each of the subsystems of that team optimizing their own part, irregardless of its impact on the other parts of the system, they started working together. And all it took was a weekly meeting, an update against this goal, and a look for how are we going to achieve the system goal by focusing the improvements on the weakest link of our product's design. It is by far the most clever way I've seen it done. And Yvette, no, I've not heard of the feasibility of objects model. If you've got a link or you could send me some info on it, I'd love to take a look at it. Yeah, so it's a way of getting the discussion going within your team in order to focus resources to where it makes the most difference for the reliability performance of your product. So let me pull up the summary slide at the end here, and there's the downloads on the right-hand side if you want to do that. There's a few links. So let's wrap it up here. I'll stay on the line for any questions or comments or stuff like that. But the idea here is just, it is really the focus of the reliability goal and the allocation is to provide a framework so you can compare your estimates and projections and test results and make decisions. Where do you put your emphasis and resources to improve your estimates or to change the design in order to meet your objectives? And then as a third outcome, it might be to change your objectives. The summary of this presentation. So hopefully that all made some sense, and hopefully a few things in there were useful for you. But that's the way I look at it anyway. Yeah, and Yvette, I'll look for your note on the feasibility of objects model for allocation. I haven't heard of that one. And I'll take a look at it and get back to you. And so can we add software to system level reliability? Certainly. So let's say it's a computer system, right? I got a motherboard, hard drive, power supply, keyboard, mouse, so on. I just create another line item or box that's software. And let's say it's there's different levels of software, but let's say it's the operating system. So here's the reliability of the operating system, and here's maybe a firmware layer that's more integrated and not seen by the customer directly, but it used to operate the computer itself. For example, making calls to the hard drive or to the memory and so on. If there's failures in that software, that can be its own box. And uh, I see it more often as that somebody will say, well, if the software is coming from the motherboard and chip there, then it's part of that piece of hardware. Some systems have broken up boards and the software goes across many different parts of your system. So that becomes a little more complex, and you may break out the software as its own box. And of course, there's products that are dominated by software, and it may have different subsystems just within the software system, and it may encourage breaking out your allocation to the various parts of your software system. Yeah, and Michael, I do try to keep it common sense. Let me see, I just saw that you've got your link there. Let me click on that, and I have no idea where that's going to open, but there it is. All right, got it. Looks like a Reliasoft site. So they probably have a model underneath it somewhere. I'll take a look at it. So yes, Gulen, you certainly can add software. It just takes a little bit of thought as to where you put it in the model. Now, if your team is organized, that they have a software engineering team, for example, is keep it as a separate box just for that team. Or if it's integrated into, say, a motherboard or electronics or into a particular part of your system, well, then it could be included in there. It's just making sure that everybody understands that the reliability associated with the software reliability is accounted for here or here in one aspect of your model. Well, Dale, I got lucky there with the focus on the mobile equipment and the car, but I get lucky like that every now and then. I just happened to find a bunch of toy images, and there was a whole series on cars, so I decided to use that analogy. It's also something a lot of us are familiar with. All right, everybody, all welcome. Let me go ahead and end the recording. Thanks so much for attending today and all the participation. I like seeing a lot of chat and input coming into it. That's a big part of what I hope to do.